Okay, so we're gonna work on this problem here. And what we're going to do is, I put the dimensions here. We have a solid shaft, AB of the pulley assembly with a diameter of 35 meters. That's the diameter of AB. So we're working on here at looking at H and K. The length of the dimensions of the assembly are on there. And the diameter of the pulley, so the diameter of this pulley is 130 millimeters. So the pulley belt tension is P equals 950 newtons. So determine the normal and shear stresses at points H and K and draw appropriately labeled stress blocks. So what we can do here is we can move using statics. These pulley forces can be moved over to act at D. So we have a Py, and then we have a Pz, and then we have a moment about X. So we're going to twist this around X when we move this. So we end up with a moment about X, which is Py times 115. Well, anyway, so we have a moment about X. Then in bending, we end up from Py, a moment about Z that's positive, and from Pz, we end up with a negative moment around Y. So this is from Py, and this one is from Pz. Okay, so that means we're going to have a bending normal stress, sigma equals m, the moment, times y, the distance from the neutral axis to the point of interest, so the radius in this case, over I, the moment of inertia of this shaft. The shear stress from bending equals the shear force times Q all over I, same I of that shaft, times T, which is going to be the thickness, so the diameter. Then we have the shear stress, which is this moment around X. It goes along the longitudinal axis. It's going to be twisting this shaft. That's the torque, which the torque just equals mx times c, which is the distance from the neutral axis to the point of interest. So again, the radius here, all over j. So I calculated I and j. Now we're going to draw free body diagrams at both of these at this location. But we need two free body diagrams because we are making an equivalent force system. So moving these forces now over to here, that creates moments there. So now we're going to have forces and moments looking right at H and K. So we have free body diagram at H and K. So we look at the forces. And here, to make any of this matter, we must draw axes. So when we're looking at this, when we're cutting it here, we're now looking at the z-axis, and it's positive to the left, and the y-axis, which is positive, straight up. Okay, and then we can label that H is here, K is here. We can put our forces on here. 950 newtons and 950 newtons. All right, so there's our forces. Then we draw our moments. So our moments are going to be, I'm going to draw another circle, label H and K, same coordinate system. We have, so we're twisting this, we have a moment in the X direction. So that's going to come out here. That's our torque. It's acting along the shaft. So this is in the X direction. Then we have a moment in the Z direction. This is from the 950 newtons times this distance. So the moment in the Z direction comes from this PY, so the distance is 230, this 150 here, and the 80 to get to H and K. So we have 950 times 230 millimeters. So we're gonna write MZ equals 218,500 Newton millimeters. And at X, this moment is 109,000. So this is 950 times 115. So we get mx equals 109,250 Newton millimeters, and then we have my equals, now we're looking at the moment that PZ has around Y. So this distance, again, is this 230. So times my, this will be in the negative direction. And that's 950 times 230. So we get the same as MZ, 218,500 Newton millimeters. Okay. So now we start looking at the stresses at point H. Stresses on point H. So if we start by looking at PY, and look at the shear stress, from PY, we would have, we cut it perpendicular to the load. So here we have no shear stress, Q equals 0. Therefore, the shear stress equals 0 from PY. Then, though, for H, we look at PZ. So now we'll have, sorry, oh no, oh, there's your, okay. So now we will have shear stress from PZ. Now we cut it perpendicular to that load at H, which H is right here. Now we're going to have a Q. Be half of this, guys, the area. That equation is Q equals 1 over 12 D cubed. So 1/12 times 35 cubed equals 3,573 millimeters cubed. Then we have tau equals VQ over IT. This is the shear stress from that shear force. We get 950 newtons times 3,573 millimeters cubed. All over the I we calculated at the beginning, 73,662 millimeters to the fourth times 35 millimeters. And we get 1.32 megapascals. That's our first stress. I find it very helpful to draw the stress block at each point. Make sure you label it so when we're looking down at HK, the axes that are coming out at HK, we have Z and we have X. So those are the axes that are going to be on this stress block. So we need to label our Z and our X. Then this is the shear stress from PZ. So I just like to draw it right on this side. I just move this shear stress, this force over to here. It's going to be pushing this way on the positive X face. So here on the positive X face, I'm going to be going to the left. Just knowing that one side means I can draw the opposite on the opposite side and then connect the heads and tails of the arrow. All right, so now I have the normal stress from the force in the y directions. This would be our bending stress. Normal stress from PY, which is the moment about Z. So this moment about Z here is going to bend this up, right? So PY is going to bend it down. Okay, so we're going to have the positive moment, so it'll bend it down like this. This is our bending stress. All right, so we have sigma x, it acts along the longitudinal axis, equals the moment about z times y, the radius, all over I. So we calculated the moment about z at that cut at HK, and it was 218,500 Newton millimeters. Y is the radius, so the diameter over 2. All over I of 73,662 millimeters to the fourth. And we get 51.9 megapascals. So that's sigma x. Then we have to determine if it's in compression or tension. We said it's going to bend like this. It's exaggerated, putting H in compression. So this is in compression. All right, the normal stress. From PZ, which would be MY. If we look at that, that would be bending it this way, which will cause a bending stress at K, but put H at the neutral axis, so Y would be 0. So here, Y equals 0. We are at the neutral axis, so therefore the moment equals 0. Okay, lastly, we have the shear stress from the torque. So it's the shear stress from FZ, or call it PZ. Sorry, it is very protective. From PZ, and that would be the moment about X. Okay, so ignore the barking. Tau equals T, the torque is just the moment about Z, times the radius over J. So that equals 109,250 Newton millimeters times 35 over 2 millimeters, all over 147,324 millimeters to the fourth, and this equals 12.98 megapascals. So then we're going to draw a stress block for this one. So we need to figure out which way this is being twisted. So PY is going to twist this whole system around that way. So that's going to twist it going in the positive x direction, it's going to go the opposite way of our bending stress. So here now, our positive x direction is going to go that way. Putting this one this way, match up the arrow heads, and then we have all of our stresses so that we can draw our stress block. See how that turns out? That didn't turn out. Okay. So we have a shear stress from bending here. So that one, we have an arrow going this way on the top, arrow going this way on the bottom. And then that is 1.32 megapascals. This is H. To make this mean anything, I have to draw the axis that I'm looking at. So H, again, when we're looking down at it, is Z and X. So same as we drew on the other stress blocks, miniature ones. So we have Z. Make sure you label your axes. Okay, so then we have the shear stress from the torque going the opposite way. There's the shear stress from bending. And that was 12.98 megapascals. And then we have this bending stress in the x direction, and it's in compression. So that would be in the x direction. And that is, so I drew that wrong on the one I posted, but it's 51.9 megapascals. So our bending stresses act along the longitudinal axis. So that's X here. Okay. Okay. So we combine those into one. And we have the shear stress is going to go in the direction of the torque shear stress because it was bigger. And then we'll have our compressive stress in the x direction. So that will be 51.9 megapascals. To calculate the shear stress, it would be 12.98 minus 1.32, and we get 11.7 megapascals. Alright, so that's the final answer for H. I'm not going to do K. What will happen at K is you will have at K, you'll have tau a shear stress from Py at K, the shear stress from Pz equals 0, the normal stress from the moment about Z at K, this will equal 0, and then at K, this will have a value, for sigma x. Shear stress will stay the same magnitude at K, same magnitude, but you'll need to look at the stress block and figure out the orientation. So I'm going to fix the solution I posted earlier today. And then I'll make a video for the second problem.